This is section 4.1, maximum and minimum values, and our first and only objective is to identify both the locations and values of a function's extrema. When we're done, I'd like you to be able to explain why the first derivative test requires continuity in order to guarantee an extreme value. This section will have some new vocabulary, and the first vocabulary is an absolute or a global extrema. Extrema is a plural for the word extreme, and if we let f be a function with a domain D, then f of c, or the output of f, or the y-coordinate of f when we plug c in, is called the absolute maximum on the domain if and only if the output for c is greater than or equal to the output for f for all other x's in the domain. By the same token, we can say that f of c, or the output of f at c, or the y-coordinate of f at c, is the absolute minimum on the domain if and only if the output that we get when we plug in c is smaller than or equal to all the other outputs that we get for every x in the domain. So what that means for us is that there can only be at most one absolute max and one absolute min. This can be a little confusing when it occurs at multiple places. So we have to be very careful that we differentiate between the function's extrema, which are the output values, and the locations of those extrema, which are the x-coordinates for which those outputs occur. For example, we can see here that this graph has 1 as its highest y value, but it's occurring at multiple locations. Similarly, this sine function has one extreme minimum, which is -1, but it occurs at multiple places. Here, if we look at a horizontal line, we have one extreme, one maximum, which is 1. That's the highest y-coordinate, and it occurs at an infinite number of places. Similarly, the minimum, which is also 1, occurs at an infinite number of places. If we look at here at this picture, we can see that we have a local minimum here, but we do not have an absolute min because it continues on forever and we never hit its smallest value. Same thing here, we can see that we have highest y values occurring at -1 and 1, and the highest y value is a 1. On this piecewise function, we can see that we never have a biggest y value because I can see that I have an open circle here at 3, so even though I can get really close to that 3, as close as I want, I can't ever really hit it. So this is not going to have an extreme maximum or an absolute global extreme, nor will it have an extreme min because we can go forever and ever down in both directions. If you recall, I told you at the beginning of the year that there would be 5 theorems that you would have to have memorized. And our first one was that intermediate value theorem, which we learned back in section 2.5 when we talked about continuity. Well, our second one is what we're going to learn today, which is called the extreme value theorem, or the EVT. And this extreme value theorem tells us that as long as f is continuous over a closed interval, then f will have both a max and a minimum on that interval. And these extreme values can occur either at the endpoints or at the interior points. So what's critical is to know that the hypothesis of this theorem requires that f be both continuous and that it have a closed domain. And the conclusion of this theorem tells us that we're going to have a highest and a lowest y values. That means the conclusion deals with the output of the function. So for example, here we have a function x squared. That's a parabola. It has no division by 0, no radicals, no logs, so this is going to be continuous at all values. But because the domain is not a closed interval, the extreme value theorem does not apply. That does not mean that we can't get maxes and mins. It just means that we aren't guaranteed a max and a min. In this particular case, we can see that we'll go up forever and ever, so we're never going to have an absolute max, but I will have an absolute minimum of 0 that occurs when x is equal to 0. If we look here, again, we have a portion of a polynomial, so it will be continuous. I don't ever have to pick up my pencil. and I'm on a closed interval, so I have to have a max and a min according to the extreme value theorem. The max in this case is 4, the highest y value is a 4, and it occurs when x equals 2. Similarly, my lowest y value in that interval is going to be a 0, and it occurs when x is 0. If we now change the domain so that it is not a closed interval, then no longer will the extreme value theorem apply. But in this case, we still get a maximum of 4 when x is 2, but we do not get an absolute minimum because we can't ever get to that 0. On this one, when the entire interval is open and I don't have a closed endpoint on either end, even though the function is continuous, I am not guaranteed a max or a min, and I don't have one. So no max and no min. We have some additional vocabulary called local extrema. So local extrema are different than absolute extrema because they do not have to be the highest y-coordinate ever. They can just be the highest y-coordinate in a particular open interval. So if we read this, it says, let C be an interior point of the domain of a function, then the output associated with C will be called a local maximum if and only if for all x in some open interval containing C, the output for f at C is bigger than the outputs that are around it. Likewise, we'll have a local minimum at C if and only if the outputs that go with C are smaller than the outputs that are around it. So when we say around it, we're talking about that open interval containing C. So if we look at this picture right here, we can see that I have a local maximum here because if I look around it in a neighborhood, I can see that the highest y-coordinate in that region is going to occur at this x-coordinate. So this is the location of a local max. For the same reason here, I can have a local min because if I look around it, I'm smaller than all those y-coordinates. Same thing here, I get a local max. Here I get a local min. It says you can extend this definition to endpoints if you use a half open interval. So that means this is the lowest value in the half open interval extending to the left, so this will be a local min. And here, again, I've got a value that is smaller than the ones that are around it. So I've got an absolute min. When we look at the entire domain, we can see that this is the lowest y-coordinate out of all of them, and we can see that I have an absolute max here on the interior because this y value is larger than all the other y values. So local extrema can also be called relative extrema, so you'll need to know that those are synonyms of each other. Just like absolute are global, well, local are also relative. And it turns out that extrema on the interior of a function occur at very specific points. So I want you to look at these interior extrema that we have above here. We've got a local max, which is inside, we have a local min that is on the interior, and we have an absolute max that is on the interior. And you should notice something about the slopes at these 3 points. Hopefully what you notice is that we have horizontal tangents or undefined derivatives at those points. So these points will now be called critical points, and a critical point is any number in the domain for which the derivative is 0 or the derivative does not exist. And these critical points or the critical numbers now become the candidates for extreme values, and you can never ever have an extreme value on the interior of a function if it does not occur at a place where the derivative is 0 or the derivative is undefined. So what this does for us is it provides us a tool that we can use to narrow our search. If we're trying to find all the maxes and mins so that we can sketch a function, we only have to look at the places where the derivative is 0 or the derivative does not exist, as long as we're on the interior of the domain. If we look at example 3 here, again we have pictures. We can see that on the graph of f of x equals the square root of the absolute value of x, we have a critical point at an interior value of x equals 0 because I've got a cusp and that derivative does not exist. Notice that this is also the location of a minimum and that the minimum value will be 0. Here, if we look at the cube root of x, we see at x equals 0 that we're going to have a vertical tangent. So the derivative will not exist here, but we don't get an extreme value because this is neither a largest or smallest value. We've got stuff that's smaller and stuff that is larger, no matter how small we make the interval containing 0. On this last one, we again have a corner, so this will be a candidate for an extreme value, and we can see that indeed, even though the derivative does not exist, we do get a lowest y value of 0 occurring at 0, and we can also see that we have horizontal tangents occurring here, which means that we will get a possible max or min, and looking at the picture we can see that we've got local maxes at both of these places. We also have absolute maxes at both of these places. Let's look at example 4, where we find the critical numbers for each of the following. Remember, critical numbers occur when the derivative is either 0 or undefined. So we will look for f prime of x, which is 24x to the 5th minus 24x squared plus 0, and we want to know when this is 0 or undefined. So we can see that I can factor out a 24x squared, and when I do that I get an x cubed minus a 1. Well, x cubed minus 1 will factor into 24x squared times an x minus a 1 times an x squared plus an x plus a 1. And when I look at this, I'm interested in knowing when this is 0 and when this is undefined, because this is when I get my critical values or my critical numbers. So I can see here that this factor generates a 0 if x is 0, this factor generates a 0 if x is 1, and this is never going to give me a 0. So I have two possible critical values coming from when the derivative is 0. If I want to find out when the derivative is undefined, I can see that this has no division by 0, no even roots, and no logs, so that means I will never have an undefined derivative for this polynomial function. Because of that, I can now say that my critical values are x equals 0 and 1. If I look at b, which is a little tricky, I will need to take the derivative using the quotient rule. So I have r prime is my low d high minus my high d low over my low squared. If I simplify this, I end up with a negative 3 over t squared. And remember, I'm interested in knowing when this is 0 or when this is undefined. We can see that fractions equal 0 whenever the top equals 0. And notice that there are no t's in the top, so there's no value of t that will make the top equal 0, which means I never get 0 for a slope on this graph. If I look at when this is undefined, at first glance I might say that t equals 0, because of course I cannot divide by 0. But we have to remember that critical values can only count as critical values if they are in the domain of the original function. And the original function has a problem at 0, so I cannot count it as a critical value. And again, I never have any undefined slopes on this graph either. Let's keep in mind that the whole goal of this section is to identify the locations and the values that are extrema for functions. So the first step in that is to identify the critical numbers. And once we're comfortable finding the critical values or the critical numbers, whichever you want to call them, we need to be able to analytically figure out whether these critical values will yield maxima or minima, and if they do, what those max and mins are. So the technique we're going to use is going to be supported by a test called the first derivative test. So again, we have some more vocabulary to go with this section. And the vocabulary is called the first derivative test for local extrema of continuous functions. So at a critical point C, that's assuming we have found all the places where f prime is 0 or undefined, then we examine whether f prime changes sign. So if f prime changes from positive to negative, then we get a local max. We can support that looking at the picture. Here my f prime is positive because my slope is positive, and then I'm followed by a slope that is negative. So I changed slope from positive slopes to negative, and I got a max at a highest value. Same thing happened here. I had a positive slope followed by a negative slope, and I get an absolute max. If, on the other hand, f prime changes from negative to positive, then we get a local min. So here we see a slope that was negative followed by a slope that was positive, so I got a local min at this c sub 3. If f prime does not change sign, then f is not going to have a local extreme. Here's an example. We're climbing to that horizontal tangent, and then we continue climbing. So we had positive slope followed by positive slope. We had no change in sign in f prime, so we didn't get an extreme value. Same thing happens here. Negative slope followed by negative slope. We don't get an extreme value. So we can apply this first derivative test also to endpoints. At a left endpoint, if the slope is positive afterwards, that means I started at a min. By the same token, if the slope is negative after, then that means I'm going to start with a max. On the right endpoint, if I fall or have negative slope prior to the right endpoint, then I will have a local min, whereas if I rise prior to that right endpoint, I'm going to have a max. So in my opinion, it's much simpler to identify these maxes or mins if we have a picture. So we're going to use that to help us as we analyze what's going on with our functions. If we look at example 5 now, which involves continuing the process that we started in example 4, the overall goal is to find the maxes and mins for a function. Then we will test the critical values and the slope around them. An easy way to do this is to draw a sign chart and label it for the derivative. So we can see that I have a number line that I can associate with f prime, and on f prime I'm going to put the critical values that I discovered, which are 0 and 1. Prior to 0, say at -1, I can go examine the signs of my outputs. So this would be positive, this would be negative, and this will be positive. So this ends up being a negative. At 0, I had a slope of 0. At 1, I had a slope of 0. If I look between 0 and 1, say at a half, this is positive, this is negative, and this will still be positive. So I'll end up with a negative slope in between 0 and 1. After 1, I will have a positive, and another positive. So I will get a positive slope. What that means for us is that my original function was falling, then it flattened out, and then it kept falling, and then it rose. So I can see that at 1, I'm going to have a min, and at 0, nothing is going to happen. I'm going to have neither a max or a min. If we look at part B, notice that I had no critical values. Because there are no critical values, there's nothing to test. And because I do not have a closed interval for the domain, that means I have no extrema on R of t. So let's put it all together. We know that the ultimate goal of this section is to find all of the function's extreme values and where they occur. So to do that, we're going to follow a set of steps. And if we do this every time, we will always be able to find the locations and the extrema for any function. The first thing we do is we will find the domain of the given function, because that helps us identify where we might have issues. The next thing we do is find the derivative of the function and determine the x values for which the derivative is 0 or undefined. These become the function's critical points. They are important, they are critical, because they are the only locations for interior maxes and mins. So the next thing we'll do is create a labeled sign chart for the function's derivative. And on that sign chart, we're going to include the domain endpoints, the domain problems, and all of the critical points. And then we're going to test the sign of the derivative before and after each interior point. Once we have step 3 done, we can sketch a rough graph of the function, and that picture will enable us to see the prospective candidates for extrema. We'll see whether the endpoints are high or low, and we'll see whether those interior points are high or low. So then, if the goal is to find the extreme values themselves, which is the outputs, then we need to actually compare all those candidates' outputs by plugging them into the function and see what comes out. Lastly, we will need to summarize either using the first derivative test or by listing all of the candidates and their outputs if I have a closed interval on my domain, or some combination of the two. So we're going to do 4 full examples to help with this. Our first one is example 6. which is to find the absolute max and min values of f of x equals x to the 2/3 on this interval from -2 to 3. So our first step was to write down what the domain is. The domain was given to us as the interval from -2 to 3. And we check to make sure that there are no problems in there. Since this is a cube root, cube roots never give us issues, so the domain's going to be everything in between those two. So our second step is then to look at the derivative of x so that we can identify the critical values. So the derivative will be that power times x to the -1/3. So that means we're looking at 2 over 3 times the cube root of x. I'm interested in knowing when this is 0 or undefined. Fractions equal 0 only if the top equals 0, and there's no x in the top. So I will never have a horizontal tangent line on the graph of this function. I will, however, have a problem at x equals 0 because that will cause me to divide by 0. And notice that 0 is still in the domain, so x equals 0 is a critical point. Step 3 is we're now going to put on a number line the domain of the function, all the domain holes, of which there are none, and the critical values. We're going to label this sign chart with an F prime so that we know we're actually talking about the sign of the derivative. If I choose a number between 0 and -2 now, so now I'm doing step 4 by adding things to this sign chart. If I plug in a -1, I will get a negative output, which means I have a negative slope. If I plug in a +1, I get a positive slope. So I can sketch my picture, which is going to look something like a fall with a corner and then a rise. So we can see that I have a possible minimum here and I have possible maxes here. So my next step is to compare the candidates' outputs. So if I look at the candidates' outputs, I'm going to be comparing f of -2 and f of 0 and f of 3. So f of -2 means I'm looking at the cube root of -2 and then I'm squaring it. So that's the cube root of a 4. If I plug in 0, I get a 0. And if I plug in a 3, I get the cube root of 9. So we can see by comparing these that this one is my absolute min, and this one is my absolute max, and this one will be a local max. So step 6 is we just summarize. We say we have a local max at x equals -2 because after -2 the slope of f is negative. We say we have an absolute min of 0 at 0 because number 1, we've listed all the candidates and it is the smallest output in the list, and we can also justify that it is a min because f prime changed from negative to positive at x equals 0. Lastly, we can say f has an absolute max at 3 of the cube root of 9. First, because we've listed all the candidates and that is the largest output that we get. And secondly, it's an endpoint that has a max value because the derivative prior to that 3 is positive. If we look at number 7 now and go through the same steps, we can see with step 1 that the domain will be all real values except for, let's see, this denominator is always going to be positive, so we don't have to worry about division, but we're taking logs of numbers, so that means this inside cannot ever equal 0. It's already going to be positive because we have absolute values, so really the only thing that's going to cause a problem for us is when x equals 0, because if I plug in an x equals 0, then I'm going to have 0, and I'm trying to put 0 inside a log, which is not allowed. So step 2 now is to take the derivative. If you remember from when we did derivatives of logs back in section 3.8, we learned that taking the derivatives of logs, we can split this up and say the log natural of the absolute value of x minus the log natural of the absolute value of 1 plus x squared. And then when I take the derivative, I'll get a 1 over x. Remember that disappears if we create the piecewise functions, minus a 1 over the inside times the derivative of the inside. If I finish this, I have a 1 over an x minus a 2x over a 1 plus x squared. Now our goal is to figure out when this is 0 and when this is undefined. And that's going to be hard to do unless we have a single fraction. So what we're going to do is we're going to get a common denominator. And we'll say 1 over x needs to be multiplied by a 1 plus x squared over a 1 plus x squared. And then we're going to say that this negative 2x over 1 plus x squared needs to be multiplied by an x over an x. If we do that and look at what we have left, we can see that we'll have a 1 plus x squared minus a 2x squared, which is a 1 minus an x squared. And on the bottom, I'll have an x times a 1 plus x squared. If we now look at when this is 0 and when this is undefined, we can identify our critical values. The top will be 0 when x is 1 or negative 1. The bottom will have a problem, or equal 0, when x is 0. But 0 was not in the domain, so that doesn't count as a critical value. With step 3 now, I'm going to create my number line, label it f prime, and put the domain problems, put the critical values, and then put the endpoints if I have them, and there are none. So now I have to test in between each of these and determine the sign of the derivative. So when I'm smaller than negative 1, say at negative 2, the top will be negative and the bottom will be negative, so the whole thing will be positive. In between negative 1 and 0, say at 1/2, negative 1/2, this will be positive, this will be negative, and this will still be positive. So I'll end up with an overall result that is negative. If I'm in between 0 and 1, say at positive 1/2, this will be positive but smaller than 1, so when I subtract I'll end up positive. This will be positive and this will be positive. And lastly, after 1, the top becomes negative while this is positive, as is this, so we get a negative. If I do step 4 now, which is to graph a sketch of what f would look like, we can see that we rise and then we fall to an asymptote because we tried to put 0 inside a log at this problem in the domain, and then we'll rise again, and then we'll fall. So we can see that f looks like it's going to have two maxes at negative 1 and 1, and we will not have a min because we keep traveling down toward that asymptote. So with step 5, we're now going to plug in our critical values and see what comes out. I can plug in a negative 1 and I can plug in a positive 1. If I plug in a negative 1 up here, I'll have the log natural of a 1/2. And if I plug in a positive 1, I get the same thing. So notice that these are both going to be extreme maxima. They'll be global maxes. And we'll say f has an extreme max of ln of 1/2 at both x equals plus or minus 1 because we don't have a closed interval, we can't just say they were the biggest numbers that came out. So what we have to say is because they are the only critical values, their outputs are the same, and f prime changed from positive to negative at x equals plus or minus 1. So with example 8, it says find all extreme values of this, and notice that it is an absolute value problem. This one is tough because it's a piecewise function and we're on a closed interval. So taking the derivative of this in order to find the critical values is going to be really hard. So let's look at step 1. Step 1 is we've got to identify the domain. Well, I have no division by 0, no square roots, and no logs. So I know the domain is going to be all real numbers in the interval that is given to me. For step 2, we cannot take the derivative until we rewrite that as a piecewise function. So the first thing we're going to do is we're going to recognize that f changes behavior at x equals 3 because that's when the inside of this absolute value changes from positive to negative, and it's also going to change behavior when x equals 6. So when x equals 3 and when x equals 6, I'm going to have changes in behavior. So that means f is going to be broken down between the values when x is between -4 and 3 and between 3 and 6, and then again from 6 to 8. So we have to decide how the absolute value behaves for numbers that are in between -4 and 3. If I'm in between -4 and 3, say at 0, we can see that this is going to be a negative number. So the absolute value will take the opposite of that x minus 3. Then I'm going to subtract what happens with this absolute value. If I plug in 0, the inside is negative, so the absolute value will take the opposite. If I simplify this now, I have a negative x plus an x gives me no x's, and I have a positive 3 minus a 6 gives me a negative 3. If I look at the next branch between 3 and 6, say at 5, if I plug that in here, I'm going to have a positive number, so the absolute value will leave it alone. And then I will subtract what happens with this one when I plug in a 5. When I plug in a 5, I get a negative number inside, so the absolute value is going to take its opposite. If I now simplify, I can see that I have an x plus an x and a negative 3 minus a 3. For my final branch, say at 7, we can see that this will be positive, so the absolute value will leave it alone. And I can see that this will be positive as well, so the absolute value will again leave it alone. If I simplify this now, I have x minus x is no x's, and I have a negative 3 plus a 6 is a positive 3. So simply looking at the function, we can see that the graph from -4 to positive 3 is going to be outputs of -3. Pretend that's down there. I got a little off. Then between 3 and 6, I'm going to have a line whose slope is 2. So I will climb 2 and go up 1, climb 2 and go up 1, and I will continue doing that until I get to 6. And once I get to 6, I'll have a y-coordinate of 3. Then I'll continue on that y-coordinate of 3 until 8. So looking at this picture, we can see that we have a min of -3 on this entire interval, and then we have a max of +3 on this entire interval. So we don't even need to do steps 3, 4, and 5, because what those tell us to do is to find. It helps us sketch the picture so that we can read off the maxes and mins. But in this particular case, it was easier just to graph the picture. So we can say f has a max of 3 on the interval from 6 to 8, and a min of -3 on the interval from -4 to 3. If we look now at example 9, we want to find all the extreme values of another piecewise function. I'm going to start with step 1 and realize that my domain is all reals because I don't have any issues with division by 0, logs, or roots. The second thing I'm going to do is I'm going to take the piecewise derivative so that I can start to examine what's going on graphically. If I have a 5 minus 2x squared and I take the derivative, I get a negative 4x. If I take the derivative of this one, I get a 1. This will be true whenever x is less than 1. This will be true whenever x is greater than 1. And if I check at 1, when I plug 1 into this, I get a 3. When I plug 1 into this, I get a 3. So my function is continuous, which is good. But if I plug a 1 in here, I get a negative 4. And if I plug in a 1 here, I get a positive 1. So the slope is not the same as I'm approaching 1 from both sides. That means this original picture is going to have a corner. So I'm not going to put an equal in under the 1s in either one of these branches because I do not have a slope at 1. It's going to be undefined. So I can write down that this is going to be 0 or undefined. When x is 0, notice I can use this because 0 is less than 1, and so I'm in this branch. This branch never equals 0, so I don't get any prospective candidates for maxes and mins from the left or the right side, and I'm undefined at that corner, which is x equals 1. So with step 3 now, I can sketch my f prime by looking at its sign chart. Domain is all reals. I've got critical values at 0 and at 1. At 1 it's undefined because I have a corner, and at 0 I get a flattening out. Prior to 0, say at negative 1, I'm in this branch, and I can see that plugging in a negative would give me a positive output for the derivative. In between 0 and 1, I'm still in this branch, but now I'm plugging in a positive number, so my output will be negative. After 1, I'm in the bottom branch, and the outputs are always positive. So I can see here that I'm going to have a max followed by a min at that corner. If I now sketch the picture, which is what step 4 is, I can see that I have a parabola that opens down, which corresponds to this rise and then a fall, and then I have a line where the pieces are connected. So I'm going to get a horizontal tangent here with a local max, and I'm going to get a local min here at 1 at the corner. So with step 5, I'm going to write the outputs of the function at both 0 and at 1. If I plug 0 in, I'm in this branch. Plug in 0, I get a 5 minus a 0 is a 5. So that is a local max. And if I plug in 1, I get a 3, which is a local min. So for my step 6, I say 5 is a local max because f of 0 equals 5 and f prime of 0 equals 0 and f prime changes from positive to negative. I can say f has a local min of 3 at x equals 1 because f prime of 1 equals undefined, but f of 1 equals 3. F is continuous at x equals 1, and f prime changes from negative to positive. What I'd like you to do is think about why with example 9 it was important to say that f was continuous.